usually like my caffeine. It like gets me going. I get excited about it, and so I'm hoping that whatever cobwebs I'm trying to shake off from my little whirlwind trip should be good. And I'm planning to just sleep in tomorrow. Let's put it that way. Um, Anyway, so that's what's up with me. Let me give you a quick little update on what's up with 250B. We're finishing up our 4th week right now. As you all know, next Thursday we have our first test. Last class, I kind of went over the Canvas page with you. I showed you all those resources. Hopefully over the weekend, you at least can get a little bit of a start into some of that stuff as you have time. But for sure, you should definitely start getting ready for the exam. My goal is to sort of finish the material today for the exam so that on Tuesday, I'm sure there'll be a few loose ends, but I'm hoping that on Tuesday, we'll have some homework to talk about. We'll probably have a group work to go over and kind of get you feeling ready for the test. I might start some new material on Tuesday, but hopefully not. It won't be that much. Mostly my plan on Tuesday will be to kind of just get everything shaped up and fill in any details, loose ends, answer questions, all that kind of thing. As for today, I will take some questions on the homework. So during the break, if you want to put any additional problems on the board over here, you can do that. What homework am I talking about? I'm talking about the homework that's due tomorrow night, which is, I think, assignment 7. Don't forget, maybe in the corner here, I should just remind you, I do have office hours today. And so today, basically, right after class, I do go downstairs for a short time, but the longer stretch of time that I'll have available will be after 5:30. But pretty much anytime after 5:30, except I go out to dinner around 7 o'clock for an hour. And then tomorrow, which is Friday, I also have office hours starting at 8 p.m. pretty much through the evening as well. So the homework is due at midnight tomorrow night. I'm pretty sure between these office hours and what we're going to do today, that I should be able to help answer most of your questions. It's a pretty quick assignment. There are a couple of conceptual questions on it, though, that you may want to ask me about if you're not sure. So that's part of why I want to be available. But you can also use these office hours just to kind of get a launch into your studying for your exam next week and ask me questions about that as well. If you want to go back to chapter 1 and review from the very beginning, I'm certainly open to questions about anything at any time. Okay, so that is kind of where we're at. There will be another assignment for Tuesday that's going to be based on what we're going to cover today. And that'll also be, of course, helpful for getting you ready for the test next week too. So in addition to starting your studying over the weekend, you will have a few problems to do for an assignment for Tuesday. Also, this weekend, be checking your Canvas email because I am going to send out an extra credit quiz that everybody who has stopped by to say hello for 5 minutes to introduce themselves can do. And that's pretty much almost everybody now. If you haven't done that yet, you still have time to just stop by for 5 minutes and say hello. That would be awesome. But I will send that out, and I'm only going to give you about a day to work on that. The quiz is not going to take very long, but I will ask for a pretty quick turnaround on it. I haven't decided exactly. I haven't written it yet, so I haven't decided exactly when I'll send it to you, but probably Saturday or Sunday I'll do that. So that's what I got down for my announcements. Does anybody have any questions about any of that? And where we're at, where we're headed here? Okay, great. If not, or if you think of something later, just let me know. On my board here, I, as usual, have put up a quick little summary of kind of where we left off on our class on Tuesday. As you can see, we're talking only about square matrices. So we don't take determinants if the matrix is a off square size. It has to be a square size matrix, but the determinant of that matrix is just a number that we are associating with that matrix. And the reason, or at least one of the reasons that we care about this, is that we can use that number, which is the determinant of A, to test whether a matrix is invertible or not. And we certainly have reasons to care about that, right? So A is invertible if and only if the determinant of A is not 0, right? So that's an important thing to know. We spent a fair bit of time on Tuesday kind of reviewing or discussing how to calculate this number. There's simple formulas for the 2x2 and 3x3 determinants that I wrote down last time. But in general, for any size matrix, we at least have this so-called expansion technique, cofactor expansion. And so it's a little bit heavy on notation with all the double subscripting and dots all over the place. But when you're actually doing it on an example, it's not that abstract. It's really quite computational. So you choose any row or any column of your square matrix A, and you cofactor expand along that row or column. And you can choose whichever row or column that you want. You'll always get the same value for the determinant of the matrix. So as we discussed on Tuesday, it's often a good idea to look for rows or columns that have a lot of zeros in them. Because if these aij's are equal to 0, then you don't have to bother calculating the cofactors, which are the cij's, right? Does everybody remember the cofactors? Cij, just to remind you here, I should have put this up probably in the recap as well. You do a -1 to the I plus j times the minor, the mij, that's where you, the mij minor, that's where you cross off row I and column j, and you find the determinant of that submatrix, right? So we'll keep practicing this, but basically it's kind of a mess, to calculate these cofactors. And you can see that there's a lot of them to calculate on any row or any column. So it would be a nice idea to choose a row or a column that has a lot of zeros in it. Right, so, but in theory, it will work for any square matrix of any size. That's right. So far, so good. Just kind of reviewing what we did last time. What we noticed, we did one example last time, is a pretty big matrix, but it was actually a triangular matrix. So remember, upper and lower triangular matrices have lots of zeros in them, right? And so when you have a matrix like that, it turns out that it's very easy to find the determinant of a triangular matrix. You just have to multiply the diagonal values. A11 times A22 times A33 and so on. It's super easy. Anybody could do that, right? So that's kind of a nice result. Of course, most matrices are not triangular, so this theorem wouldn't directly apply to them. But somebody made a suggestion to me on Tuesday, I think, in class, about possibly taking a strategy of putting more zeros into our matrix by doing elementary row operations, right? So we've learned in chapter 2 how to do EROs. And if we do EROs, we basically bring the matrix into a triangular form. And then we'd be able to find the determinant of it really easily. So I want to pursue that today. I want to explore that as kind of a starting point, which is, could we maybe do EROs to our matrix, which in turn might allow us to take advantage of a matrix that has lots of zeros, maybe even fully triangular. And so that's a good starting point for today. So how do EROs affect the determinant of A? This is the question. So we'll start with this because we didn't get to this last time, but this is going to be a reasonable strategy here. Okay, so the idea is, yeah, we'd like to do EROs on the matrix, but we have to be aware of how those EROs could potentially change the determinant, right? So I'm going to actually go through all three of the ERO types that we have learned about. There's the permuting of two rows. There's multiplying a row through by a constant. And then there's where we add a multiple of one row to another. So let's talk about it. Let's suppose that we start with some matrix A and we permute two rows. I don't know which rows, I'll just call it Pij. So suppose that you permute two rows of a matrix. Well, then it turns out that the new matrix, which I'm calling B right here, the new matrix has a determinant that picks up a minus sign. Okay, so for permuting two rows, we have to be aware that we will cause a sign change on our determinant. We saw on Tuesday that one of the big challenges with determinants is not making sign errors, right? Because these -1 factors are always kind of floating around in the calculations. So you have to be a little bit careful. And here's another place where we see a minus sign coming into it. Okay, the second one, if we start with A and let's say we multiply the ith row through by K. So this was the second ERO. You take your matrix A and you multiply one of its rows through by K. In this case, guys, the determinant of B will also pick up that factor of K. It will also pick up that factor of K. That actually should be pretty obvious. Because if you take all of these Aij's, let's say you multiply the ith row by K. If you put a K in front of all of those Aij's, if you scale each of them up by a factor of K, well, then the whole expression here is going to have a factor of K that has been introduced into it. And so the final determinant of the new matrix should just be K times whatever the old determinant was. So that's, I think, pretty reasonable as well. And then finally, the third ERO is where we start with our matrix A and we do the adding operation. So this is where we take A sub ij of K. So what we're doing here is we're taking K times the ith row and adding it to the jth row. Well, I have a little bit of good news on this one. It turns out that if you do that ERO, nothing changes. Nothing happens. The determinant of B actually just stays the same as the determinant of A. Okay, so if we know these effects that the EROs have on the determinant of a matrix, we can keep track of how the determinant got affected through a process of bringing a matrix into triangular form. Okay, so I'd like to do an example to kind of show how we could maybe try this strategy out. Now, in my example, I'm only going to use a 3x3 matrix. You guys all know from Tuesday that for a 3x3 matrix, we can just use the arrow method. It's a pretty easy method for finding the determinant, but let's pretend we're not going to use that. I want to illustrate this sort of higher perspective of determinants here with this example. So let's take an example here, and it is going to be use EROs to find the determinant of A where A is equal to, I'm going to squeeze my matrix right into here if I could. This is just going to be a 3x3 matrix. The first row is 2, 1, 3. The second row is -1, 2, 6. And the third row is 4, 1, and 12. So let's go ahead and practice how these EROs affect the determinant of a matrix. So I'll do the solution here. Let me grab a blue marker for the solution. Right, so we're going to start with A, as you would expect, and we're going to hit it with some EROs. Would somebody like to suggest an ERO to start off with on that matrix that I just put up here? Go ahead, Brian. You can permute second row to the first row. Okay, so permute the first two rows. That's P1, 2, and that gives me a -1 in the top left corner, which is a pretty good number to have up there. The first row goes to the second row. Everything else, third row, just stays the same. Okay, I like that. Would anybody like to suggest another ERO? I could multiply the top row by -1. Actually, I'm not going to do that. It's not wrong what you said. If I was actually trying to get the matrix into row echelon form, we learned that pivots have to be 1s. But I'm not actually trying to go for row echelon form to use this theorem. I just need it to be triangular. And for a triangular matrix, there's nothing that says the diagonal values have to be 1s. So although it would not be wrong, and if we were doing, you know, a process of EROs normally to get row echelon form, I probably would use the ERO that Reed suggested. But would there be something else that we could do, not worrying about that too much? Yakko?
Just multiply two on the first row and then add it to the second.
Okay, doing the adding operation. So I'm gonna do A1, 2 of 2.
Do the same thing to the last.
Same process for the last row, exactly. So A1, 3 of 4. I'm gonna do both of those together, right? So the first row stays the same. But the second row, if I take 2 times the first row and I add that to the second row, I'll get 0 and 5 and 15. And if I take 4 times the first row and add it to the bottom row, I'll get 0, 9, and 36. Okay, so that does look good so far to me. Okay. Now it's not quite in triangular form yet, but we're getting there, right? Would somebody who I have not heard from yet like to suggest an ERO that I could do from here? Adrian.
By the bottom row by 1/9.
Okay, I could multiply the bottom row by 1/9. So that's M3 of 1/9. So we have the first row staying the same, the second row staying the same, and the third row is 0, 1, and 4. Again, I personally probably would have chosen to work on the second row before I work on the third row, but we can always do what I'm going to do next, which is permute the second and third row. So now I'll go ahead and permute the second and third row. And it looks like this. It's still not triangular though, guys. So we're working a little bit hard here to get it into triangular form. What would be the best ERO to get this thing into triangular form from here? Homan?
Multiply the third row.
No. Jose?
You can multiply -5 and add it to the third.
Use the adding operation between rows 2 and 3 with -5. Yes, take -5 times the second row and add it to the third row. So I'm going to keep the first row the same, which also keeps the second row the same. And now -5 times the second row added to the third row is 0 and 0 and -5. That look okay? That is triangular, and that's what I've been aiming for here. So we have a triangular matrix, which means we know what the determinant of this matrix is, right? The determinant here would be what?
Diagonal.
Which would be?
5.
5, right? So I'm using the theorem that the determinant of a triangular matrix is just the product of the diagonal values. So we get 5 right here, -1 times -5. And now the determinant I actually want to figure out is this one. Find the determinant of A. So I actually have to take this result, and actually, this is important, guys. I have to go backwards through my work. See, we've got some bookkeeping here that we've done. We've written down what all of our EROs are. We know what the effects of those EROs are, but we're now tracing backwards through these steps. So let's be careful as we do that. If this determinant was 5, what would this determinant have been right before it? Also 5, because the operation that took us from here to here is the one that has no effect at all on the determinant, right? So if this one is 5, then the one right before it would have to have been 5. Okay, now if this one is 5, I'm going to keep going, then the one right before that would have had what value for the determinant? -5, because the ERO that took us from here to here was the permuting operation, and that costs us a minus sign. Okay. Now, so if this determinant was -5, now the question is, what would this determinant have been? And this is the tricky one.
-5/9.
You would think that it would be -5/9, but it's not. Because, guys, when I wrote down this second step, I was going from left to right, and I was saying, starting with A, if I multiply a row of A through by K to get B, then the determinant of B will pick up that factor of K. But guys, we are tracing our work backwards right now. So if this determinant was -5, then this is what happened after I had multiplied by 1/9. So instead, when I go backwards, instead of multiplying by 1/9, I actually have to flip that over as a reciprocal, which means I'm going to multiply by 9 and I'm going to get -45. Does everyone understand that? We're going backwards through our bookkeeping here. Now, I have to be clear, there are some situations where we're not going backwards. And so if we're going forwards through our EROs, keeping track of the bookkeeping, then we do multiply by literally the number that's right here, which is K. Everybody with me? It depends whether you're going forward or backwards, is my point. Okay, so this one is -45. So then let's keep going. What would this determinant be? Also -45, because the A operation has no effect on the determinant, according to my third item over here. And if this one is -45, then let's trace back one last step. The original matrix A would have what determinant? 45. Okay, there's a sign change, right, with the P operation, the permuting. So we get a final answer of 45. Does this make some sense? I should mention here, that you're not committed to doing a full blast ERO approach to finding these determinants. Let's say that you're starting with this matrix and you do, say, up to here. And you say, okay, I realize that this matrix is not triangular yet, but it's got more zeros in it than I started with. Let's just go ahead and cofactor expand column 1, or maybe now we decide we're going to use the arrow method, whatever. We could just say, you know what, I'm going to bail on doing any further EROs. Even though it's not triangular yet, you can bail at any point and say, you know what, I'm just going to calculate this one directly. And if you did that, you would have gotten -45 right here. And then you would just be tracing back just this portion of the work. You see what I mean? You don't have to go whole hog in on one method. So you can say, I'm going to do a little bit of cofactor expansion, and I'm going to do a little bit of EROs, and I'm going to kind of mix and match the techniques a little bit. That's also totally fine. Okay? So the whole idea here is that another tool for doing determinants is to bring more zeros into the matrix through EROs. And if you want to, you can go all the way to a triangular matrix, which is what we did in my solution here. But you wouldn't have to do that. You could just say, I'm going to go part way, and then I'm going to stop. And I'm just going to do the determinant from there. Nothing wrong with doing that at all. Everybody okay? Are there any questions on this example? Okay, we've got 3 properties of determinants kind of right here on the board with these effects of the EROs. While we're kind of thinking about that, I'd like to add a few more properties that you might be interested in. So let's just make a little additional list here of more properties of determinants. Because we didn't have time to do this on Tuesday, so now is as good a time as any to add to our list more properties of determinants. I'm just going to continue my numbering right where I left off. So we have 1, 2, and 3 are over here, and now I'm just going to continue my list. The first one is that if you transpose a matrix, so if you calculate A transpose and you would like to know what the determinant of that matrix is, it turns out that actually transpose also has no effect on the determinant. So if you swap the rows and columns, it makes no difference to what the value of that determinant would be. I sometimes will get people asking me, well, we see how row operations affect a matrix. What about column operations? You might wonder about that. We haven't talked about doing column operations on a matrix. Technically, we don't do those. We only do row operations. But if you wanted to, you could take your matrix, transpose it, which effectively swaps rows and columns, and then the row operations that you are doing on A transpose are effectively doing column operations on A. So that's part of what this property allows you to do, is to say, okay, I could, if for example, you can see that from one matrix to another, that two columns have been permuted, right? Technically, that's not gonna fall under any of these. But now we kind of know that, well, if you permute two columns, that's like permuting two rows of the transpose. And the transpose matrix has the same determinant as the original matrix. So you can still take advantage of the knowledge that you have about row operations as they would apply to columns as well. So it's just kind of nice to know that. What else do I have on my little list here? Let me see. What do you think would happen if we took the determinant of, let's say, K times A? So if we had a matrix A and we multiplied it through by K, do we have any proposals for what this formula should be, maybe? Adrian?
So A squared times the derivative.
Why are you saying K squared? What's that? The homework. What if the matrix was, I think the homework was a 2x2 example. What if the matrix was n by n? But it's good that you're doing the homework early and that you've got that in your mind. That's a really good idea. Say it again. That's it, guys. It's a little bit easy to mess this one up. It's actually K to the n times the determinant of A. Now, why is that? Well, because if I multiply one row of A through by K, there's a factor of K that gets picked up. But of course, if you're taking the entire matrix and multiplying it by K, you are effectively taking every single row of the matrix and hitting it with a factor of K. So that's n rows. So you get n powers of K on that, right? That makes sense? So this is super easy. Let me just over on the side here, guys, a quick little example. If A is, let's say, 4 by 4 with determinant of A equal to, let's say, 5, then what is the determinant of 2A? I've been known to put these kind of little questions on my exams. It's kind of a theoretical question. And the popular wrong answer, of course, is to say it's 10. They'll take the 5 and the 2 and multiply them together. But it's actually not 5 times 2. It's 5 times 2 to the 4th. Because it's a 4 by 4 matrix. So all 4 rows of A would pick up that factor of 2. So 2 to the 4th times 5 would have been 80, I believe, instead of 10. So you pick up a much larger answer there. So it's good to be aware of stuff like that. So that little example goes with item 5 in my list here. Okay, let's do another one, number 6. If I had the determinant of A times B, so if I multiplied two matrices together and I wanted to find the determinant of that, this one is really nice. It's what you would think it is. It's just the determinant of A times the determinant of B. So you just multiply the individual determinants together to get the final determinant. Okay, so that's pretty self-explanatory. It's actually kind of hard to prove. I'm not going to do it right now, but it's an easy one to remember and to get right. Let's do number 7. Do we think that there might be a formula for the determinant of A inverse? This, of course, assumes that A has an inverse. I'm wondering if anybody might have any Before I write down the answer, does anybody want to guess what the answer is? Marco?
1 over the determinant of A.
That is absolutely right. This is 1 over the determinant of A. That turns out to be the correct answer. Notice, by the way, if A is not invertible, you would have had a determinant of 0. So if the matrix is not invertible, then the determinant would be 0, and you're already looking at this denominator like, oh, well, that better not be 0 on the bottom. Well, good news, it won't be. It won't be, because if the determinant of A is 0, you're not even going to be talking about A inverse. So this property won't even apply. Does anybody think they might know why that formula is correct? Could we justify it, I wonder? Do some examples. See if it works 3 times, it must be good. All Saturdays are sunny, so the next 3 Saturdays are sunny, so that must be a correct statement. I don't know. In terms of any other property on that board, could we justify number 7 based on anything else that's in that list? Holman?
What about A times A inverse is the identity?
That's it. So remember, guys, A times A inverse is equal to the identity.
Yeah, the determinant of the.
Yeah, we could just take the determinant kind of both sides if you wanted. What is the determinant of the identity matrix, by the way? The identity matrix is as triangular as it gets, and the diagonal values are all 1s, right? So the determinant of the identity matrix is just 1. And then if I use property 6 to split these 2 parts up, then I have determinant of A times determinant of A inverse equals 1. And so now you see why the determinant of A inverse is just 1 over the determinant of A. That's exactly right. Yeah, so that's another good one. Let me see. Do I have? I do have a red marker. As I have a warning here. This is not number 8, but I'm going to add one more thing in this list. This is sort of the one that doesn't work, which is that around this time, people will be asking me, okay, we know the determinant of transposes, inverses, products, and all that. So the question is, what would be the determinant of A plus B? And the reason I'm putting it in red with a big warning around it is that the trouble is determinants do not play nice with addition. There is no formula that we can write down. Nothing jumps to mind. Nothing would necessarily be true there. So if you see addition or subtraction of matrices and you're wondering if determinants play nice with that, unfortunately they don't. They don't. So there's nothing very easy that we can say about that. Okay. I think I've highlighted the properties of determinants that I want to. Are there any questions so far, guys? They hanging in there? How am I doing? Do I seem kind of tired today? Or is the math really doing the job of the drug that I told you about? It like wakes me up. I just love it. Well, guys, another question you might have. Now, this was a good one. How do EROs affect the determinant, and what are the other properties of determinants? But another question you might be having right about now is, gosh, Dr. Annan is spending a lot of time talking about this one number that we are associating with a matrix. And so far, that's a lot of work. Cofactor expansion, EROs, all this stuff. It's a lot of work to come up with one number that's just going to be this test formula. So a question that some of you might be asking is there anything else good about determinants? Is it really just trying to figure out whether we get 0 or not 0? Like, so, okay, so this matrix has a determinant of 45. All right, great. So that means it is invertible. But does it mean anything else? Like, does it tell us anything else other than just sort of thumbs up, thumbs down on the invertibility question? And the answer is there is actually a whole lot more to this story. And I'd like to tell you a little bit about this, why determinants are important. So we'll just do a quick little chat about this. Remember, we are in the mindset of up with determinants, right? I don't care what that guy at San Francisco State says. There's lots of good things about determinants. So here we go. Why is the determinant of A important? I want to give us something that we can really sink our teeth into here on this. So the first one, of course, I'm just going to recopy it for, just so your notes are nicely organized. So I'm just going to rewrite down that it is a test for invertibility. And that is, of course, a good reason. That is a good reason in and of itself. So we'd like to know that. But there are some other things I'm going to add to this list as well. Okay. Like, does the 45 actually matter for this determinant right here? If I had gotten 46 as the answer, would that have made any difference in my life at all? Right? Or, you know, what, like the actual number, does it mean something? So it does actually. So it offers an alternative method for finding the inverse of the matrix if it exists. Meaning, as long as this is not zero, as long as the determinant is not zero, then A inverse exists, and we can actually find A inverse purely using determinants. We don't actually have to do the Gauss-Jordan method that we did in the last chapter. So this is going to be a new method, which I'm about to explain. It's called the adjoint method for A inverse. Okay, so I'll explain more about that in a minute, but let me get the whole list down first, and then we'll come back to some of these points. There is also a way to use determinants exclusively to solve systems of equations, right? They're solving for the unknowns in a linear system. So forget EROs, forget the augmented matrix and all that big process with pivots and back substitution and all that stuff we learned in the last chapter. We can avoid all of that if we want, as long as we know something called Cramer's rule. And this is for a system. A times X equals B. So there you go. You have a linear system of equations. You would like to solve for the unknowns. Turns out you can do that using determinants. Okay. Now, I should mention, before you throw the EROs out the window and the augmented matrix and the thing about pivots and free variables and back substitution, before you get rid of all of that, please don't. Because this is only going to apply, of course, if A has a determinant. And that will only happen if, for one thing, A has to be a square size. We've seen lots of linear systems already this semester that are not square system. The coefficient matrix is not a square matrix. So if your matrix is not a square matrix, then it doesn't even have a determinant. So it really isn't going to be something that's suitable for using determinants. So we've got to know the old stuff too, right? This is not intended to be a pitch that we can just like throw out everything we've learned so far in the first 4 weeks and just go with this, right? We do need to know the older stuff too. Okay, finally, one last point. If A, this is really more focused for smaller matrices. If A is 2 by 2 or 3 by 3, then it turns out that the determinant of A has a geometric significance. There's actually, we're not going to be doing a lot of geometry in this class, but there is an insight that this determinant will give us about, so this number 45, you got a 3 by 3 matrix here, right? This 45 means something geometry-wise. Specifically, it has to do with volume. of something. So we talk about areas and volumes, points being collinear or coplanar, things of that nature is kind of what I'm getting at. But before I give like the full-blown explanation of all that, I've got to kind of sort of slow down a little bit. And I'm just going to say here, see below, because now what we're going to do, guys, in your notes is we're going to explain the second, third, and fourth points kind of one at a time here. Okay, so I'm going to start, if we have time before we take a little break here. I'm going to start with item 2. So what is this adjoint method for A inverse? So this is another application of determinants. Okay, so the way this works, I just need to write down a definition here to get us started. So given the matrix capital A, which is n by n, like always, has to be a square size. Given our matrix, if we replace every entry of the matrix A by its corresponding cofactor. The cofactors, you'll remember, those are theCij's, right? So if you basically build this matrix, just fill it up with these cofactors, we get what is called the matrix, right? The matrix of cofactors. And I'm going to be denoting that M sub C. The matrix of cofactors. This is M sub C. So just to be clear, right, you basically have this matrix. It's the same size as A. It's still n by n. But what you're filling it up with are the cofactors of A. So with the subscripts lining up to the positions in the matrix. So it's just an n by n matrix that's filled up with cofactors. It's an n by n matrix filled up with a bunch of cofactors. So you just lay those all out there. Sorry, the last column is CNN here. And so we really should have drawn C1n and C2n in that last column, just to make it look nice. That would be the matrix of cofactors. Before I actually go on, why don't we do an example of this? So let's just take a matrix and see if we can find its matrix of cofactors, just so we have an example to kind of look at. Let me grab my matrix here. Okay, I'm going to use a 3 by 3 matrix again. So let's let capital A be the matrix 2, -3, 0, and then 2, 1, 5, and then 0, -1, and 2. We'll just use a 3 by 3. It's a good size to play with. And I would like to find, right, I'm going to find the matrix of cofactors for this matrix. Okay, so again, the way you do this is you just go through and you calculate all of the cofactors. And there are 9 of them. In the 3 by 3 matrix, there will be 9 cofactors. So everybody ready for this? How do the cofactors work again? What you do, it's going to be the same size matrix as A. What you do is you find the minors by crossing off a row or a column. I recommend, by the way, that you do this in pencil or something that, or at least do it very lightly, because you're going to need to cross things off several times because you've got several entries to calculate here. But yeah, so you calculate the minors by crossing off a row and a column and taking the determinant of the submatrix. And at the same time, we have to remember that there are sign changes in the odd positions, right? Everybody remember this from the other day, right? I like to draw this little diagram for a 3 by 3. It would just look like this. So be sure that once you have calculated the minor, if you're in one of these positions where I've got this little minus sign change, you have to put that sign change into your answer, okay? So let's try it. Let's see how we do with this. The 1-1 cofactor here. Okay, I'm gonna talk about the 1-1 cofactor. How do I do that? I cross off the first row and column. I take the determinant of the 2x2 matrix that is left behind. And for a 2x2, we remember, I hope that the determinant is just AD minus BC. So that would be 2 minus -5, which is actually 7. And then that would go as the 1-1 cofactor, and there's no sign change in the 1-1 position because it says plus here. I don't change the sign at all. You with me? Let's do the 1-2 cofactor. Now you see why I want you to do this lightly, because I need to uncross the first column, and now I'm gonna cross off the second column. Now I've got these 4 numbers. So 2, 5, and 0, 2. Can somebody tell me what is the cofactor C12?
0.
It's not 0,
4.
and it's not 4.
Negative 4.
Say it again.
Negative 4.
-4. It's really 4. So you're talking about this matrix here, right? That's the submatrix. The determinant of this is 4, but I'm in an odd position of the matrix. So instead of writing down 4, I have to write down -4. I have to do a sign change on that. So it would be -4. That look okay? Let's try the 1-3 cofactor. Now I'm gonna cross off the third column in the first row, and I'm gonna work on this little 2x2 right here. And what is the 1-3 cofactor gonna be based on that? -2, right? -2 minus 0 is -2, and we do not make a sign change on the 1-3 position. Okay, the sign changes are just in these positions only. Okay, let's do the 2-1 cofactor. So now I'm going to be crossing off row 2 and column 1. I have these 4 numbers here. I might write it down over here, -3, 0, and then -1 and 2. What would be the 2-1 cofactor? This determinant is actually -6. So do I put -6? I got a minus sign there, so I have to change it to +6. Exactly. Okay? At this point, I've got so many lines through my matrix, it's a little hard to keep track of. The 2-2 cofactor, well, if I cross off the middle row and column, I'm only gonna keep the far corner numbers, right? And what's the determinant of the far 4 corner numbers? 2 times 2 minus 0 times 0, so that's 4. And there's no sign change on that one either, like so. The 2-3 matrix, let's see, the 2-3 cofactor, I cross off row 2 and column 3, and I'm gonna write down the matrix that would be left over, 2 and -3, and 0 and -1. What is the 2-3 cofactor going to be? It's going to be +2. It looks like -2 when I do this determinant, but I have a sign change there. You guys getting it? Okay, if you're getting it, I'll go a little faster. The last row, of course, I'll be crossing off the bottom row and each of these 3 columns. I think we should have -15 in the lower left corner, and the lower middle corner, we should have 10, and the lower right corner, we should have 8. I believe I mentioned at some point this semester that I occasionally make mistakes on purpose just to see if anybody's paying any attention. Okay, yes, guys, it should be -10 because there's a sign change on that bottom middle entry. So -5, -10, and 8, that's your matrix of cofactors. I know this seems like, gosh, this seems kind of tedious, but this is already 90% of the work to finding the inverse of A using the adjoint method, because there's not much more that you have to do. Let me show you what the rest of it is. So I've given the definition of the matrix of cofactors. Now I'm going to make another definition, which is the adjoint of A. the adjoint of A, and this is written ADJ of A, is, and here is the formula, it is just ADJ of A, and this is going to be the matrix of cofactors transposed. We're going to transpose the matrix of cofactors, and that will give us the adjoint. And that's an easy thing for us to do. It's easy to transpose a matrix. So in our example above, so example for capital A above, let's write down the adjoint of A. The adjoint of A is simply the transpose of the matrix of cofactors, which just means I swap rows with columns, right? So the first row becomes the first column, 7, -4, and -2. The second row becomes the second column, which is 6, 4, and 2. And the third row becomes the third column, -15, -10, and 8, just like that. Okay? And if you're with me on that, that's an easy step, then we can write down the adjoint theorem now. And the adjoint theorem is going to explain how to get A inverse. So let's just do it right here. We don't need much space for this either. So I'm just going to call this the adjoint theorem. Right, and what it says is that if A, which is n by n, is invertible, if we have an invertible matrix, then this is going to be a formula for A inverse. So then A inverse, here's the formula. We have to take 1 over the determinant of A. That's just a number so far. And of course, that will not be 0 on the bottom if A is invertible. And then what do we do with, the rest of this? We actually just multiply it by the adjoint of A. You just multiply it by the adjoint of A. So all we have to do, let's go back to our example one more time. Let's see if we can figure out the, I don't know why this is erasing so badly. Let's see if we can figure out the inverse of our matrix A there. I've already got the adjoint. The only other thing I need, according to this formula, I just need the determinant of A. So we go back to A right here, which you can barely see, and we just need to find the determinant of A. So let's do that. So example, find A inverse for the matrix above. Right, so we just have to find the inverse of it. And for that, I'm going to just need I've already got the adjoint, so I just need the determinant of the matrix according to my theorem here. And so what that would be, the determinant of A, let's write down A again, 2, -3, 0, 2, 1, 5, and 0, -1, and 2. So we just write down the matrix we've been working with. And what's going to happen here, if I want, I could just use the arrow method on this one. So I would probably do that. The first column is 2, 2, and 0. The second column is -3, 1, and -1. And I'm going to do my arrows. Might as well practice this again today. First arrow gives me 4, right? Second arrow gives me 0. And the third arrow gives me 0. All right, so I'm multiplying those diagonals, and then I go the other way. So I subtract this way, that's also 0. And then the next one is minus, let's see, -1 times 10, so it's minus -10. And finally, minus -12, exactly. And if you work all of that out, guys, it turns out to be 26. Turns out to be 26. So if that looks good, then we can write down A inverse using this formula right here. So let's do it. So A inverse do this, then we'll take a little break, okay? So the A inverse is 1 over the determinant. The determinant was 26. And then we multiply that by the adjoint, which we worked out just over there, 7, 6, negative 15. And then the next row is negative 4, 4, and negative 10. And the bottom row is negative 2, 2, and 8. It is perfectly okay to leave the answer like that. If you want, it's not wrong, and I guess I'll just do it just to show it one time. You can throw that 1 over 26 into all of these entries by just putting it as a denominator here. You don't have to do this. I'm doing it because I just want to make a comment here in a minute. So here is the inverse of A. Right? The one and only inverse of A. It's always unique. Now, because it's unique, you know that this is the answer that has to be right. And you can imagine having done this the Gauss-Jordan way. The Gauss-Jordan way would have been that you start with this matrix and you augment it with the identity matrix and you do EROs and you get the identity matrix on the left side, the inverse of A showing up on the right side. Does that look like that's going to be a great afternoon of calculations to get this as the answer? I always talk about trying to avoid fractions. But guys, if A inverse has fractions in it, you're going to get those fractions. You're going to have to live with that. And one of the nice things about the adjoint method is it sort of pulls the denominator out, right? This determinant of A is out in front, and you have a very nice clean matrix that just has the cofactors in it. So it's one advantage, I would say, of the adjoint method. I usually don't ask test questions where I say, use the adjoint method to do it. I'll usually just say, here's a matrix. I want you to find the inverse, and I'll let you choose the method that you want to use. But in this kind of a situation, I think this method would be preferable here. Yeah, okay. So that's number 2. That's the adjoint method for A inverse. By the way, this is, I probably should do it. Maybe I'll do it on Tuesday, explaining this formula. It's not actually that bad to sort of justify it. So for right now, let's just take it as a freebie, as a given. And if I have time on Tuesday, kind of as part of our reviewing and everything, I might explain it. I will point out though, that if you do a 2 by 2, if you do the 2 by 2, and you remember the formula when we wrote it down originally, we swap the diagonal entries and we do sign changes on the other 2 entries. This formula is exactly compatible with that. The determinant of A is AD minus BC. And if you start calculating the cofactors of this matrix and transposing them, right? If you calculate the transpose of the matrix of cofactors for a 2 by 2 matrix, this is what you're going to get. Everybody in this room could check that. Guys, the 2 by 2 matrix, its cofactors are, what are they? They are 1 by 1 submatrices, right? Like, what's the 1, 1 cofactor? The 1, 1 cofactor, cross off row 1 and column 1, it's D. And look at that. The D has shown up in the 1, 1 position. So it's completely compatible with the matrix of cofactors approach. Yeah, Mark.
So in another scenario, if you go the 4 by 4 matrix, we would have to use the cofactor expansion for the determinant and then multiply that by MC, which is the matrix of cofactor.
Absolutely. If it was a 4 by 4 matrix, I think Marco's looked at my sample test or something like that. If I give you a 4 by 4 matrix and I ask you to find the inverse of it, I'm basically going to be asking you to find the determinant of a 4 by 4 matrix. That's in the denominator. And then 16 cofactors here. That's what it would be. That's a lot of work. 16 cofactors. Each one of those 16 cofactors would be a 3 by 3 matrix, right? So if I told you that I regularly put that on my exams, would you believe me? You wouldn't, would you? No, that would be way too much work, but you know what I can do? That would be a reasonable amount of work. I could give you a 4x4 matrix and ask you to tell me one specific entry of the inverse matrix. I could pick any entry I wanted. I could just say, tell me what is the, so I'm just gonna scribble here for a second. You don't have to take any notes on this. When you do the review materials, you're gonna see this, because I do like to do these questions. Just make any old 4x4 matrix. It would be unreasonable for me to ask you to find the inverse of this using the adjoint theorem, right? It would be way, way too hard. Way too time consuming. But what if I asked you to find, I don't know, find the inverse, just the 2-3 entry. Just the 2-3 entry. Now, why am I saying that that would now be reasonable? Well, to get the entries of A inverse, they all have determinant of A on the bottom of them. You see, they all have 26s on the bottom here. So to find this, you would have the determinant of A on the bottom. So that would be a 4x4. You'd have to pick a row or a column here and do the cofactor expansion. Or you could do the ERO thing that we did earlier, where you bring some zeros into the matrix. But you'd have to figure that out. But you would not have to figure out 16 cofactors on top, would you? Because I'm only asking you to find one entry here, the 2-3 entry of A inverse. What would that actually be, by the way? What would be the numerator of this fraction? I'm writing down a fraction here. What would I be putting on top right there? I don't want to know a number. I want to know, and it wouldn't be 10, by the way. But I don't want to know the number. I want to know what would be the expression for it. Yes, that's what I'm, not the A inverse of 3, 2. But you are swapping the subscripts, which is correct. That's because, it's because of this, guys. The numerators of your entries of your matrix, what are all of these numerators here, guys? All of these numerators are just the different cofactors, but they've been transposed, right? In this adjoint method, we had to transpose these cofactors. So what that goes in the numerator here would have been C32. You know what? I think I am going to write this for your notes, because I have come to really like these questions, and I want to make sure you can do this. So basically, here's a little remark. The IJ entry of A inverse is given by, here it is, CJI divided by the determinant of A. So if I give you a 4x4 matrix and I want to see if you can work with it, I could basically ask you for one particular entry of that inverse. You know that all of the denominators are determinant of A. There's a 26 on the bottom of everything in that matrix. And then what's on top? It's just a cofactor, but which cofactor is it? It's the transposed cofactor, because the numerator has adjoint of A in it, and the adjoint of A is the transpose of the matrix of cofactors. When you transpose the entries of a matrix, you swap those subscripts. So instead of Cij, it becomes CJI. That makes sense? Yeah, so I think there's one of those on the homework for next Tuesday as well. So questions here, guys? After the break, I'm going to explain the Cramer's rule, and I'm also going to take any other questions on the homework that's due tomorrow night. So you feel free to add more problems on the board during the 10 minutes, but let's take a break. I'll let you get some water, take a run around outside if you'd like, and I'll see you at about 11:15.
Okay.
It would just be a number, yeah, you'd just be, this thing here? Yeah, it would just be a number, like if I asked you, what is the one entry of A inverse in this matrix? It would just be 7/26, so you just leave it like that. Yeah, exactly. You can just express it as a fraction. That makes sense? Okay, great.
I remember when I connected them.
And he goes through that, so it's like, I'm thinking of. But like, I didn't know. Last class, I was like, she puts the notes anyway, I don't even have like, I'm not even gonna take those, you know, they hear it. I think it probably a little more. Taking notes. If he takes notes on like the. Go fast, so it's like, when I'm writing on the notes now, I'm not thinking that's. I don't understand what. Yeah, I was in that class with you guys. I switched out to the 10 500 kid. Dude, I feel so lucky, it's like, it's so fast, and I'm like, she's doing this in August. Really? Yeah, I'm like, all the time, I'm like, dude, right now. Yeah, but it's like, I don't know, that class is so, like, last time. I didn't get it. I was like, I'm not even gonna take it. I saw you with your phone. Takes you close to it. And I was just like, look, you know, and it's make a little more sense now, but it's confusing. And it is. Really good. I mean, it's the graveyard. I don't know if it's like.
Any plans for the weekend, Keone? No.
All my exams coming up, so. it's-
Good answer. Time to hunker down on it. Yeah. Mhm. I hear that. After what I did yesterday, now I'm ready to just kind of have a nice, slow, quiet weekend. Yeah. Yeah, normally I would never have gone and done that, but it's like, it was my last chance to kind of go do that before the weather changes.
Yeah.
So, yeah. What's going on, Reed? Sorry?
Chemistry club upstairs.
And, chocolate mountain. Oh, they have food up there?
Chemistry club, they sell over heaps now.
Oh, how nice.
So are you gonna be in your office right after class?
Yeah, and at some point I want to get take my little lunch break, but for the first half hour, I'm always there. And then if people get their questions answered, then I can go have lunch at 12:30.
Okay. Well,
But that is like half the assignment.
if you explain 32, 35, 30, then
Yeah.
I won't have to go down there.
Oh, okay.
Those are my questions.
Yeah, we'll most likely be able to do that. So I'm actually doing great. I don't have that. All I have to do is explain the Kramer's rule.
Okay.
And that's not very long, so I think we're gonna be good.
Nice.
Yeah. I try to be helpful. Sometimes I'm actually successful at that. Somebody is using these wipes on this board. I think that's what's, well, look at that board up there. It's all smudgy.
Yeah.
Last year, I actually took the disinfectant wipes thing out of the room and I took it down to my office.
How are you sick with that?
Because I knew that this is causing the problem. People use these on the boards and they think they're cleaning the board, but actually it makes it much worse.
How do you clean it then?
there is actually a whiteboard cleaner, like an actual thing you can buy that the math department has. But unfortunately, most people don't pay careful attention with that, so it is what it is.
Like I said,
Lecture classes on like Tuesday, Thursday. Classes on Tuesday.
Yeah, yeah, but that's by choice. Used to be, I would have 4 days a week. But the classes were half as long. So it's the same amount of time in the class. I asked them, could you please consolidate my schedule? Because I do tend to go mountaineering on weekends. Not every weekend, but I just like to have that block of time available. So, I have a very heavy Tuesday, Thursday, because I got in like 9 a.m. for office hours. I won't go home tonight until after 10 p.m. I mean, I have a couple of breaks, but I have this class, then another one at 2, and then another one at 4. So I'm on my feet a lot on Tuesdays and Thursdays, but then I have like the other days to recover. It's actually like the schedule this way better.
Yeah,
Uh,
because people used to have like this class 4 days a week.
They used to do that. In fact, it used to be more common. I actually think students have been part of the shift because students were like, I don't want to come on Fridays, like every 4 days out of 5 every week. So the students were sort of always signing up for the 2-day sections, and the faculty or the administration started to figure that out. So, oh, well, maybe we should everybody will be happier if we only make everybody come 2 days instead of 4 days.
I think that's better. Yeah. Much rather-
I personally would have had a hard time for 2 hours in a class, like trying to focus on it.
It is better.
I mean, I try to give the 10-minute breaks and all that kind of stuff, but I could see myself just having a hard time with that. Depending on what the material was and the professor and everything, I could see it being really a drag to go for 2 hours, and then also the other problem with it is, okay, so then after your last class on Thursday, you don't have another class till Tuesday. So you have to stay really motivated over the weekend, or else you're gonna come back the next Tuesday and be like, huh, what was I? Yeah, what I said.
It was Tuesday through Friday.
It was actually the way they used to do it was it would either be Monday, Tuesday, Wednesday, and Friday, or it'd be Monday, Wednesday, Thursday, and Friday. They would always give like a Tuesday or a Thursday off, which for me wasn't good because I never had free time. Like I had to always be on go. This was like 20 years ago, like before when I first came here, before COVID and kind of much more traditional style. Yeah. Nowadays, I think there's more flexibility.
Guys support those.
Yeah, they even, like that first week, I was able to just have you watch videos. Before COVID, I would never been able to.
Really?
Yeah.
They like mandating you?
Yeah, I gotta come into the classroom every single time. And if you're not there, then you have to have a sub. So somebody else has to come. And I didn't like that because I would never know exactly what the sub did. Whereas having you guys watch a video that I made, then I know what you saw. Yeah, so I think that there have been some. Yeah. Yeah.
Is that like a grad student or something?
Actually, usually I would try to get another professor to do it and then I would trade them back sometime. Actually, I have like 4 or 5 professors that owe me at this point. Because I was always subbing for people and then I was never missing my own classes. But it was just kind of like you do a favor for your colleague kind of thing. So, but now I don't have to do that. I make a video.
I'd be sad if you were messed up because I'd be like, this guy's so cool. And then so much.
I don't know. You'd be like, oh, thank God I don't have to take that guy's test. Oh, boy. All right, guys, I think, oh, yeah, probably so. I see quite a few, problems on the sideboard over here. If we do all those problems, everybody's gonna pretty much have the assignment done. Actually, we might have a fair bit of time. I just want to explain the Kramer's rule first, and then after that, we can go ahead and take a look at some of the homework problems as well. So let me explain Kramer's rule. Remember, I had that list of why determinants are important. So we had the test for invertibility, then we had the adjoint method for finding A inverse, and now I want to go to the third thing that was in the list, which is Kramer's rule. And I actually have to tell you, I did not used to cover this in this class, but I have so many of my engineering students who the following semester, they're over there taking whatever it is, engineering 308, or I forget what the number of it is some class, and they would come back to me because it was a linear algebra thing, and say, hey, what is this Kramer's rule thing my professor's doing? I guess they're assuming you guys have seen that over there. So I decided, I guess I better put it in my lectures. So that's what I'm going to do here. This is Kramer's rule for solving A times X equals B, right? So I've now started using this in my class so that you guys will know what's going on when you're over in your engineering class. Remember, this only works if A is invertible. So this has to, of course, be n by n, has to be a square size. And even more than that, it actually has to be invertible. And the goal is to solve for the unknowns. Now let's remember that if A is invertible, how many solutions will we have for our system? So if we have an invertible matrix out of these three outcomes, what's the number of solutions? 1, right? Just 1. So when I am solving for the unknowns here, there will be one unique right answer. There will be, okay? So the way this works, guys, is that Kramer's rule tells you what each unknown is as an individual formula. Okay, so in this case, what we get is the formula for the ith unknown is, it's written, I'm going to write it as x sub I, because that would be the ith unknown. And this is supposed to be something that is totally in terms of determinants, not doing any EROs or the Gauss-Jordan method or the Gaussian elimination, just in terms of determinants. And it is going to look like the following. The determinant of A goes on the bottom again. And again, red flags will come up if A is not invertible. You're going to be like, doesn't make any sense, right? Actually, if A is not invertible, you might have no solutions to your system. So, it wouldn't make sense to think that there would have to be a formula. But as long as that's not 0, we're good. And then what we put on the top is another determinant, and it is the determinant of capital B sub I. And I need to explain what that is. So this is capital B sub I, where B sub I is the matrix obtained from A by replacing column I with the B vector that is on the right-hand side of your system. Okay? So you replace the right-hand side with the B vector. So it's another n by n matrix that has just one column that's been changed from the original. Okay, so that's it. That's the whole Kramer's rule. Let me do an example to just show you how this works, but it's not hard. It's not a difficult thing. It's mostly just calculation. So let's do an example here. Let's solve for Z. And here's the system. So we have 2x and then plus 8z plus w equals 0. Leave a little space there in front of that 8z though, because I also have a y variable. The next one is negative x plus y plus 3z plus 5w equals 0. And then the third equation is 2x plus 2y plus 6z minus w also equals 0. And then the last one is 3x plus z minus 4w equals 7. So let's take that. So it's an entire system. You could write down the A sharp, you could do your elementary row operations. But if you did that, you would presumably solve for not just Z, you'd solve for X and for Y and for W also. So this is kind of a clue that we're really in the realm of Cramer's rule, because he's just looking for one of the unknowns specifically. And Cramer's rule really highlights the specific solutions for the specific unknowns. It's not like find the entire X, Y, Z, W. I'm only asking here for the Z variable. Okay, so one of the things that we obviously have to do, guys, for the solution is we need to write down the matrix A, the coefficient matrix. So let's just do that first. It's a 4x4. You notice I'm giving you a 4x4 matrix here. So 2, 0, 8, and 1. And then -1 and 1 and 3 and 5. And then the coefficients on the third row would be 2, 2, 6, and -1. And on the fourth row is 3, 0, 1, and -4. So that would be the A. We're also going to need to know what the B vector is. This is the so-called right-hand side vector. Those are just the numbers on the far right of the equal signs. So that's just going to be 0, 0, 0, and 7. And before I actually get into the Cramer's rule, I know I'm going to need to find the determinative A. So let's just do that first. Okay, we'll just get the determinative A figured out here. And to do that, well, it's a 4x4. So I don't have the arrow method, right? We can't do that. So what we have basically is cofactor expansion. And we might as well practice it. We haven't done it today, so let's just practice. Does anybody want to suggest a good choice of a row or a column to do this expansion on?
Second.
The second column has 2 zeros in it, right? So that would be the best one to minimize the calculation. Yes?
Are you able to do EROs first to add more to them?
So we could do that, right? That's actually what I was pitching earlier today, right? I sort of said, hey, you could add more zeros to your matrix by doing EROs. I think in this case, since I haven't practiced cofactor expansion with you guys today, that I'll just do it that way. But you're right, we could certainly do EROs on this, but I'm gonna just go ahead and just go straight into expansion on column 2. And I'm choosing that column not because I have to, but just because it makes my life a little easier to have 2 out of the 4 entries being 0. So you remember how does the formula look for this? This is going to be A21, C21 plus A22, C22 plus A32, C32, and then A42, C42. All of the second subscripts are the 2s, the column values. Okay, and A1, A2, A3, and A4, those are these numbers right here. So what we can do is get rid of the A21 term, because we know that that's 0, and the A42 term is also 0. The other thing I like to do is I like to, I mentioned this on Tuesday, I like to get those sign changes. Remember that the cofactors, which we see here, they pick up minus signs if the subscripts add up to an odd amount. And so the C32 is going to need to have a sign change. Let's go ahead and incorporate that now. So the A22 is 1 times C22, and then the A32 is 2 times C32. But then I'm going to go ahead and incorporate the sign changes and write them in terms of minors. And when I go into the level of the minors, I have to do sign changes on the odd ones. So I have a minus on that M32. Okay? Now I just have to find these values. M22 is the determinant of the matrix that we get when we cross off row 2 and column 2. So I cross that off and I leave myself with 2, 8, 1 and 2, 6, -1 and 3, 1 and -4. Leave a little bit of room to add those columns. I'm going to use the arrow method in a minute, but let's just finish writing out what this second determinant would be. The M32 we're just crossing off row 3 instead of row 2. So now I have to get rid of the, do this lightly on your paper, guys, or else you have to rewrite the matrix so you don't get confused by all the crossing lines. But if I cross off row 3 and column 2, then I have 2 times the determinant of, well, it would be 2, 8, 1. And then -1, 3, and 5. And then 3 and 1 and -4. Okay, so I just have to do a couple of arrow method calculations on these 3x3s. So just to practice that again, I'll recopy the first 2 columns of my first matrix here and start going to work with my arrows. So my first diagonal is 2 times 6 times -4. That would be -48. And then the next diagonal is -24. And the next diagonal is +2. And then I start going the opposite direction. 3 times 6 times 1 is 18, but it's with a minus. And then 1 times -2 times, 1 times -1 times 2 is -2, but that's subtracted. And then 4 times 2 times 8, I believe, is 64. So minus -64. That's the first one. Okay, let's put some brackets here. And then we have -2 times whatever we get for the second one. And maybe without recopying I don't have a lot of room here. I'm just going to write down the 6 terms. 2 times 3 times -6 is -24. And then 8 times 5 times 3 is 120. And then we have 1 times -1 times 1 is -1. And then I subtract the other diagonals. So -3 times 3, -5 times 2, and then -8 times -1 times -4, that's -32. And that is just a big bunch of numbers to be worked out. And I am going to save the headache of doing that in our head. This just comes out to be -110. I'll let you check that one just with a calculator. You can get the value. It doesn't matter too much. I just want to have a number to play with here. Okay, so I think that should be it. So now I want to get back to the Cramer's rule. Here's our system, and we'd like to solve for z. According to our Cramer's rule, the values of the unknowns are just fractions based on the determinant of a underneath and then the determinant of b sub I. Which b sub I do I want if I'm solving for z? It's the third one, right? If I think about the unknowns, they are x, then y, then z, and then w. So the B3 is the relevant matrix for solving for z. And then how do we do it? Well, what's it say over there? Replace the third column of A by the B vector. So here's A. I'm just going to replace the third column by the B vector. Okay, so I can do that. That's not too bad. I have a 2. Well, let's just do it column by column. The first column is 2, -1, 2, and 3. The second column is 0, 1, 2, and 0. And then the fourth column is 1, 5, -1, and -4. And then we're just going to replace the third column with the B values, which were 0, 0, 0, and 7. So that's how the B thing works. And we do need to find the determinant of that matrix now. So the determinant of B3. And for that, so for the determinant of this matrix, is everybody clear how I got this? It's just taking the original A that's in the bottom right, this one right here, and replacing this column by this column. So I'm just inserting this into there. That's it. So you see it right here, the third column, like so. Now, when I want to do this determinant, I might as well expand that third column. Adrian? Because my unknowns, why do we choose the third column? My unknowns are x, y, z, and w, and the z is the third unknown. It would be like playing the role of the x3. If this says xi right here, but of course that's referring to one of my unknowns. So the third unknown is the z variable. If I have been asking you to solve for y, then we would have put this 0007 into the second column. Make sense? Okay, sweet. Okay, so here we go. I'm going to expand, I'm gonna do it quickly too, guys. I'm going to expand column 3. The new column that we just added is what I'm going to expand. So the reason for that is if I go along column 3, I have 0, minus 0, plus 0, and then minus 7 times the determinant of the matrix that I get when I cross off the row and column that the 7 is in, and we're left with the determinant of 2, 0, 1, negative 1, 1, 5, and 2, 2, negative 1. Okay, so what is this going to be? Well, we have negative 7 out in front. And again, I can just do my arrow method. I'm going to do this quickly just to save a little time. For my arrow method on this one, the first diagonal is negative 2. Second diagonal will have a 0. The third diagonal will be also a negative 2. And now I subtract going the opposite direction. So minus 2, minus 20, and minus 0. I did that fast, I know, but it's nothing too difficult. I think that's negative 26. And what is 26 times 7? I wrote it down here somewhere. 182. So this is negative 7 times negative 26. So I believe, I know I went fast, but unless I screwed it up, I think it's 182. And so therefore, excuse me, Z is equal to 182 divided by negative 110. Okay, does that seem okay to everybody? Excuse me. So that's just what Z is. It doesn't help me find X or Y or W, but maybe I only care about Z in my physical problem. That's okay if there's just one unknown that you care about. Question, yeah.
I got a little lost.
You're Oscar, by the way, right?
Yeah.
Okay.
I
you're-
got a little lost when we did how can we cross out from the next row? Like, what was it?
When I'm expanding the third column, right? So technically the formula is A13C13 plus A23C23, A33C33, and A43C43. And A13 is 0, A23 is 0, A33 is 0, A43 is 7, but it's being multiplied by this cofactor. When we calculate cofactors, we have to take them, basically the minors, and those are determined by crossing off the row and the column that corresponds to the subscripts you're working with. Make sense? Great. Good question. Are there any other questions here so far? So I've explained 3 reasons why determinants are important. They test for invertibility. We now have an adjoint method for finding an inverse of A that is totally determinant based. And now we have a third application, which is Cramer's rule for solving these systems of equations. I had a 4th thing in that list, which was something about geometry for 2x2 and 3x3 matrices. I'm going to come back to that, but that's really not a topic for today. I think I'll save that one. That's really more relevant for chapter 4, actually. So we'll kind of touch on that, I think, as we sort of move into the next part of the material. What I'd like to do with the time we have left today is help you with some of this homework. To make it, the more I can help you with the homework, then the more time you have to focus on studying for the test as well. So might as well consider that a win-win. So let's do a quick look at some of the homework. I may not get to all of it because there's quite a few things over there, but I'll do what I can. How's that sound? Let's start with 3.1. And I'm just gonna sort of kind of go in order probably. So 3.1, this is for the homework that's due tomorrow. And so the E and F, those are true, false. And what it says on part E is basically determinant of A plus B equals determinative A plus determinative B. All right, based on what we said earlier today, is that true? No, remember it was the warning item in my properties of determinants? Yeah, this is not true. This is false. And guys, what you need to do if it's false, what are you supposed to, I want you to write down this. An example. I would like an example, 2 by 2 example. I promise you that almost anything you make up, you could get unlucky, but almost certainly you just put in any random numbers and you find the determinative A, you find the determinative B, and it won't be the same as if you added the matrices and found the determinant of that. So just show the calculations of it. Okay, I'd like everybody here to make their own example. So I don't want to like just put one thing down and have everybody turn it in. You can't hardly mess this up. You just pick numbers and calculate what the determinants of everything is. And I bet you're gonna see that it doesn't work. If you get unlucky, just try it again. You can't mess it up, or you can't get unlucky that many times. Okay, part F. Part F just says that if all of the entries of A are positive, so I'm gonna just be brief here. So if we have numbers throughout this matrix that are all greater than 0, does that mean that the determinant of A is greater than 0? So if there's no minus signs in the entries in the matrix, would that guarantee that the answer for the determinant couldn't have any minus signs? I don't think so, right? I don't think so. So this is also false. And again, I just want you to give me an example. My phone. Sorry, can't answer it. Anyway, so that's also false. Let's see, 54, what is 54 about? Oh, yeah, 54 just says if we start off with, 54 is kind of a little proof. If you start off with the 2 by 2 matrix, and here's how those entries might look, right? A11 and A12 on the first row. On the second row, A21 and A22. Then what they're asking you about is they're asking you to verify that the determinant of CA would be equal to C squared times the determinant of A. That's actually consistent with I think, again, when I made that list of properties of determinants, the determinant of a constant times a matrix is equal to the power of that constant, which is based on the size of the matrix, times the original determinant. So how do you do this problem? Well, you need to write down what C times A is. So you could do this, you could just go ahead and write it out. You're just gonna put a C into all of the entries here. CA11, CA12, CA21, and CA22. And now you just have to find the determinant of this. Well, the determinant of that, we have our 2 by 2 determinant formula, right? So upper left times lower right minus upper right times lower left. Well, you can see what's going to happen, right? You're going to get C, a little bit more room, I guess. You're just going to get CA11 times CA22 minus CA12 times CA21. Sorry, 1, 2, and 2, 1 down here. Like that. If you just factor the 2 C's out, you've got C squared here and here. If you just factor that out, right, you're just going to get C squared times A11, A22 minus A12, A21. And what's in brackets? What is that expression in brackets going to be the same as? The determinant of A again. Yeah. So this is just C squared times the determinant of A. So just a calculation really for a 2 by 2 determinant. That's kind of what they're looking for there. And it foreshadows that property that we wrote down more generally in class today. Okay, let me see if everybody's okay with 3.1 so far. None of these are really that bad. I want to do 22 from the next section though. I think it's a good one to understand the concept of it. Yeah, so let's go to 3.2, number 22. And what they give you here, I actually have to write this one probably all the way out because it's got some equations in it. So on 22, they give you, x1 plus 2x2 plus kx3 equals 0. And then they give you another equation, which is 2x1 minus kx2 plus x3 equals 0. And then 3x1 plus 6x2 plus x3 equals 0. And by the way, I know that maybe not everybody has done this problem yet. We're getting a little further into the assignment. It's totally okay if you just want to focus on listening to the solution, but definitely your goal here should be really to understand these problems. This is not just, oh, I'm going to do the homework so you don't have to do anything. This is, I'm going to do the homework so we can really make sure we understand the problems, right? So definitely, want you to kind of take it with that point of view. It says to find the values of k. So find k. See, there's a k as a coefficient here. Find k such that we get infinitely many solutions. Now, if this had been in the last chapter, we would have written down our augmented matrix. We would have tried to do EROs on that and get it into row echelon form and then look at the pivots according to what k is, right? But this is in the chapter on determinants. So I'm kind of thinking that maybe we could use determinants to help us with this. What are the possibilities again for how many solutions any system might have? 0 or 1 or infinity. These are the options for any system, right? In this particular system, though, I claim that only 2 of these 3 options are even possible. And do you see why I say that? You have to have the trivial solution. Everybody can see if you put 0, 0, 0 for all of the x's, that it works. So this system will not have no solutions. It doesn't even matter what k is. For any value of k, you would never have no solutions. And the other way to think about it is that if you did put it into an augmented matrix, your far right column would be all zeros because of the right-hand side being all zeros. And if you do EROs on that, the far right column stays as all zeros the entire time. And that means, guys, if your matrix looks like this, you will not get a pivot in that far right augmented column, no matter what you do. You cannot have that happen. And if there's no pivot in the far right column, then you're not in the zero solutions case. So these are your choices. This system, depending on what k is, this system will either have one solution or it will have infinitely many. Does anybody remember the situation that we talk about for when there is one unique solution to the system? I know that that means there's no free variables. But what would be true about the coefficient matrix? I guess that's what I'm getting at. For a system that has only one solution or exactly one solution, what do you know about your, in this case, 3x3 coefficient matrix? The 3x3 matrix, that's an n by n matrix. So in the back flap of my book, I've got my big long list, A, B, C, D, E, F, G, H, I, on and on and on. It was called the invertible matrix theorem. When you have an invertible matrix, you'll have one solution. So this would be if A is invertible. And if I'm asking find k such that there are infinitely many solutions, well, that would just be A is not invertible. right? That would just have to be when A is not invertible. And how do you test whether a matrix is invertible or not?
Determinant.
Take the determinant. And what if the A is not invertible, what should the determinant be?
0.
0. Exactly. So guys, all you're gonna do here, all you're gonna do on problem 22 is you're gonna write down this coefficient matrix. I'm kind of scribbling here, so you're gonna have to take my notes and write it up a little nicer later on. But you just take this coefficient matrix, you write down the determinant of it. You can use the arrow method if you want, whatever method. It's just a 3 by 3, and you're just going to set that equal to 0. So you just want to know, when does that determinant equal 0? Because that's when A is not invertible, and that's when you'd have infinitely many solutions. I think you're going to get a couple of different values of K when you do that one. But that's how you do it. So it's kind of, although it's computational, it is conceptual as well. We had to talk about some of the concepts here to really understand that one. Okay, so far so good? Okay, let's see. We've got three more problems here from 3.2, and they're all kind of the same idea. They're all kind of on the same theme. So with the limited time I have, I might just pick one of them. Let me pick 35. I think I'll do 35, and then I'll leave 30 and 32, I guess, for you guys to think about. They want to know that, so that what they tell you is that if you start off with, and we're gonna do a group work on this next Tuesday as well, but if you start off with this matrix, this 3 by 3 like that, they basically say as a given that the determinant of this matrix is -6. So then they're gonna ask you to find the determinant of this matrix, DEF, -3A, -3B, and -3C. And then G minus 4A, H minus 4E, and I minus 4F. So there's sort of two ways to do this problem. The not so nice way, the way that doesn't really teach you anything and is just kind of a pain, is to like say, oh, I'll do the arrow method on this. And you write out the arrow method, and you get a bunch of terms, and you somehow try to match it up with what the arrow method of this would give you. And it's just a big alphabet soup of notations and symbols and stuff. So I would not recommend doing that. There's a better way to think about this problem, and that is that you might just notice that some EROs have been done to the original matrix to bring you to here. And we talked today about how the EROs affect the determinant. So you can just imagine you started with A and you asked yourself, what happened to it? Well, I see that the first two rows kind of got switched. The DEF is now on top, the ABC has been moved down. So I kind of see a P12 going on there, right? And then I don't know what you want to call it. I guess you could call it P1 for the time being. And then once you've permuted the two rows, the top row is DEF, but I see that there's also a factor of -3 that we didn't have originally. Okay, so there must be M sub 2, right, of 3 probably happened there, and that gave me B2, some other matrix. And so now the first two rows are good, and then the third row, it started off GHI, and now what is it? Well, it's -4 times what was the first row. Did I just copy this?
You forgot a negative. I think we did. M2.
Oh, this is M2 of -3. That's one mistake, but let me just see, did I?
On the bottom left, it should be G minus 4.
Oh, this is 4D. Yeah, that's what I thought. Okay, 4D. I made a little typo on when I wrote this down. No big deal. But what I see here is this looks like the original GHI row, but with the DEF row added to it. Like, so it looks like I did some kind of an A operation, right? With the DEF row to the, I guess actually the DEF row is now the first row, not the second row. It doesn't really matter. The point is there's no effect of the determinant from this. I think it technically would be A13 of -4 to get our final matrix, which the book is calling B. And the question is, what's the determinant of this matrix B? So now be careful here, guys. The one I did earlier today, we were doing the backwards bookkeeping. We ended up with a triangular matrix and we went backwards through our work. That's not what we're doing here. Here, we're actually literally starting here with something that we already know, which is -6. And we're just going forward through these EROs. So the permuting, that does a sign change, right? And then multiplying the second row by -3 really does multiply by -3 as I go from left to right. And then this one has no effect at all. So the final answer, I think, on this one should be, unless I screwed anything up, should be -18. That look all right? So that's how it goes. I do think on problem 32, really quickly, and then I know I'm out of time. I think that actually the rows and columns have been transposed. So you're gonna need to use the fact on 32 that transposes have no effect on determinants. So that might help. Guys, we got it almost all done. I'll leave you a little bit to do on your own for tomorrow night, but I have office hours if there's anything else. And study hard this weekend, see if you can get a good jump on getting ready for our testing. Thanks, everyone. I'll see you soon.
I did develop.